I guess I'll get started. So today we're going to do fusion trees, but before I do fusion trees, I just wanted to say one thing about Van Em Boas trees, which we did last time. So somewhere in there, so we did Van Em Boas trees, and then we did Y-fast trees, and they got the same bound. The argument, so for Van Em Boas trees, I mentioned instead of using arrays, use hash tables, and then you'll get O of n space instead of O of u space. Okay. It turns out that there's something. So it turns out that there's even an exercise in CLRS, exercise 20-1 part F, which says exactly that. Prove that if you use hash tables instead of arrays, you get linear space. And what I told you is actually their intended solution. But it turns out that there's an error. There's a very subtle error. So the argument that we discussed in class that gets O of n space is not really O of n space. It's slightly worse. And it's not just the argument. It actually doesn't get O of n space. So that's going to be a p-set problem. I'll tell you exactly which sentence I said that was wrong, and you have to tell me why and fix it. Okay, so. But you can get O of n space, and you'll see that on the p-set. Okay, so and Y-fast trees, as I described, actually do get O of n space with this indirection. Okay, any other questions before I start? Yes. Okay, so now we'll do fusion trees. So fusion trees. Remember, we're solving the predecessor problem. This is due to Fredman and Willard in, I guess, 93. Right. And we're going to look at the static predecessor problem. Okay. Later, after their paper, it was made dynamic. So there was a paper by Anderson and Thorup. So here we have Anderson-Thorup. And they got an update time of log base W of n plus log u, or log n, sorry, updates. Okay, and it's deterministic. And then later, Raman. Oh, and are you scribing today? Okay. Got log base W of n updates. And this is expected running time. So it's a randomized algorithm. Okay. In all cases, the query time is O of log base W of n. Okay, so I'm going to show you just the static version, not these two, that gets query log base W of n. And there's going to be some polynomial time amount of pre-processing. It actually won't be that bad, but it'll be more than sorting time to actually create the data structure given the static points in the data structure. Okay, so that's why you can't use it for sorting. It's something we talked about last time. But you could use the dynamic versions for sorting. Okay. So the basic idea of fusion trees are to have, instead of binary search trees, to have k-ary search trees where k is bigger than 2. Okay, so we're going to have, so a fusion tree looks something like this. Okay, so actually, just a show of hands, who here has seen or heard of either 2, 3, 4 trees or B trees? Okay, so a large number of people, but not everyone. Okay, so the basic idea is going to be as follows. Let me actually write it a different way. every node is not going to have one key, but it's going to have, say, roughly k keys. Okay, so we might have 5, 15, 27, 32, and 48. These are sorted. Okay, and hanging off this is going to be a subtree of everything that has a key less than 5. Hanging here is going to be another tree of everything between 5 and 15, everything between 15 and 27, etc. And then there's a node here. There's another big fat node here, etc. And then each one of these branches in many directions as well. Okay, so that's the basic idea behind these, having larger arity trees than just binary search trees. Okay. Yeah. So these are sorted. So everything hanging off here is less than 5. Everything hanging off down here is between 5 and 15. Right. So in a binary tree, there's just a single key in the node, and to the left is bigger, to the left is smaller, to the right is bigger. Okay. Okay. So so we're going to have this basic structure with k being theta of w to the 1/5 keys per node. Okay. So, what is the height of this tree? If you have, in general, in terms of k, what's the height of this tree? Yeah, log base k of n, right? And that's, so we're having, so that implies the height is, well, it's of log base w to the 5th of n, right? But if you just remember what your log arithmetic, this is the same thing as log n over 1/5 log w, right? Which is just the log base w of n. So this is why we're hoping to get log base w of n. Okay. But there's of course a problem here, which is our time is not just the depth of the tree. We have to also take into account how much time we spend at each node of the tree, right? So kind of naively, what you might think to do is start at the left and then go see where I am, and then go down. Okay, that will take you k time per node, so you get k times log base k of n, which is always worse than log base 2 of n. You could do a binary search, then you would get log k times log base k of n, and the log k's cancel, and you just get log n again. Okay, so really, to make this work, really, we can only spend a constant amount of time per node. Okay. Now, does anyone see something that's like blatantly, something that just simply can't work about that, right? How are we going to spend, there are w to the 1/5 keys in here, okay? How much space does each key take? Not log w, but w. A key fits in a word, right? So the amount of space to represent a node is w to the 6/5. We can't even fit it in a single machine word, so how can we process it in constant time, right? That's so we're going to have to develop some techniques to get around that. Okay, so the basic issue is how do we search a single fusion tree node in constant time? Okay. So with Van M to Boas trees, using the word RAM model, we exploited the fact that keys were themselves also kind of memory addresses, and that's how we were able to beat this comparison-based lower bound. Here we're going to go way more overboard with using the power of the word RAM model. Okay, so you're going to see a lot of bit tricks in this lecture. Okay, so the basic ingredients. Okay, well, we're going to use multiplication. We're going to exploit the fact that we can multiply numbers in constant time as long as they fit in a word. You'll see where that's going to come in. In fact, there is a version of fusion trees which avoids multiplication, which came later, but I'm not going to present that. We're going to see sketch compression. So there has to be some amount of compressing of the keys because we just said that all k keys can't even fit in a single node, so we can't hope to do it in constant time. We're going to have to somehow compress these keys. And we're also going to see word level parallelism. So at some point, when a query comes and reaches a fusion tree node, we have to see where it fits, which subtree we have to recurse to. And we're going to eventually do that by comparing with all keys simultaneously using a constant number of word operations. Okay? And somewhere in there, we're going to also look at, well, there's going to be a very basic subroutine we're going to need, which is the most significant set bit. And we're going to show that we can do this quickly and that we can use it to do some of the other things we want to do. Okay, so I mean, just so we're all on the same page, in a W-bit word, how long does it take you to find the index of the most significant set bit? With any algorithm. W, right? So what do? You kind of loop from the W minus first bit all the way down to the 0th bit, and then you do a bitwise and mask out that bit and see whether the result is 0 or not. Okay? So can you beat W? Give me anything to beat W. Okay, how would you do log W? Yeah. And so yeah, you do binary search to figure out what's the largest I such that your number is bigger than 2 to the I. And 2 to the I is just one bit shift I positions to the left. So that's all constant time per iteration. So we're going to see this in constant time. Okay, we're going to show that in the word RAM you can actually do most significant bit in constant time. Okay, that's going to be, and it's not going to be as easy to explain, but we'll do it. Okay, so yeah, right. I think about it though. When I say constant time, like on your computer, you'll probably never deal with types that are bigger than 64 bits, like 64-bit ints. Log of that, I guess, is 6. We probably will have a constant number of operations, but I think it'll be more than 6. We'll count what it is. We'll count what it is when we get there. But if ever you deal with like 1024-bit ints or something, then or no, maybe larger. I don't know what we'll have to do to beat the log W, but okay. So good. So let's start attacking these things. So how do we search a single fusion tree node in constant time? Well, before we get there, we need to make sure that we can even fit a fusion tree node into a single word. Okay. So here's the basic idea. So remember that I'm not counting really pre-processing time. This is a static data structure. I'm allowed to do whatever computation I want. Okay. So the first thing I'm going to do in the very beginning is just sort everything, okay, and then just build the tree with exactly k nodes per internal node, okay. And then now I know what the nodes are, what the elements are in a particular node, and I want to figure out how to form that node to fit in a single word. Okay, so let's focus on representing a single fusion tree node. And it contains k keys x0 less than x1 less than dot dot less than x sub k minus 1. OK. So let me draw a nice picture to convince you that we can get away with using less than w to the 6/5 bits to represent a single fusion tree node. So let me draw a path. So let me first write this 1, 0, 1, 1, 1, 0, 1, 0. OK, so let's say that that's some element. That's one of the xi's. OK, so I'm going to first draw a vertex here. And then I'm going to go from the least significant bit to the most significant bit. When I see a 0, I go left. When I see a 1, I go right. OK, so I see 0. I see 1. 0, 1, 1, 1. That's 0, 1, 1, 1, 0, 1. OK? And then there might be some, there are some other xi's in here. So there might be another one that looks like this. I guess 0, 0. Well, let me draw it. So OK. So what's this? This is 0, 0, 0, 0, 0, 0, 0, 0, 0. That's 5 zeros. And then a 1, and then a 0. And then I might have another one that maybe branches off somewhere down here. OK. So I can draw some collection of, so for example, here, k is 3. So I have 3 xi's that I'm representing in this way. Okay. And the thing to note in this picture is that in order to differentiate, right, so in order to differentiate the xi's, I only need to look at vertices where there's actually some branching, right? So for example, this bit, so this is the second bit, like this is this bit here, and also this bit, which is the 0, 1, 2, 3, 4th bit, 0, 1, 2, 3, 4th bit. Just maintaining those, remembering those 2 bits is enough to differentiate all the xi's. OK? So I can define, so let me write let r less than k be the number of kind of branch bits, and let their indices be b0 less than b1 less than not less than br minus 1. So these are kind of the only bits I need to know in order to distinguish the xi's. And if I just project down to those bits, then it maintains the ordering of the xi's. Okay. I mean, we're not, don't worry, we're not anywhere near done. There's a lot to, there are going to be some issues that we're going to see very soon. And I'm going to define a sketch sketch sk of x as keeping only the xbi. Okay, so for example, I mean, it's a function also, the sketch function depends on the whole set of the xi's, because it depends on this picture. So for example, sketch, in this particular scenario, if I'm sketching 1, 0, 1, 1, 1, 0, 1, 0, I'm saying I only remembered that bit and that bit. That's just equal to 1, 1. OK? So so now going back to fusion tree nodes even fitting into a single word, each xi has sketch of xi taking r, using up r bits, but r is just at most k minus 1, so that's also w to the 1/5 bits, implies can store all of the sketch of xi's in k times r, which is O of w to the 2/5 bits. Okay, so at least the information can fit into a single word. Okay. Now there are going to be some issues, like for example, there's no C operation which, so we could easily mask out in pre-processing. We could create a mask, right? Each fusion tree node could store the mask which tells you what the important BIs are, and you can convert xi into just remembering the important bits by masking out everything else, right? Just anding with the bits that matter. But that's not going to compress things. That's not going to remove the bits that don't matter. And there is no C operation which says compress into these bits and put that into a new word. Okay, so we're going to have to deal with that at some point. There's probably a more serious issue, though, which is that the query element doesn't need to be one of the xi's, right? So let me draw an example. So let's say there are 4 bits. Okay. So imagine that the xi's that we're actually storing are the following. One is 0, 0, 0, 0. So W here is 4. One is 0, 0, 1, 0. One is 1, 1, 0, 0. And another is 1, 1, 1, 1. Okay, so in the tree, the things that matter here are so what are the branch bits that we're actually going to remember? Well, there's a branching right here. And there's a branching right here. It's the same bit, actually. And there's a branching at the root. So there are two branch bits. Okay? So it's the 0th bit. 0, 0, 0, 0, 0, 0, 1, 0. Okay, so sorry, here I was, forgive me, I'm imagining that I'm reading from the left. Okay, so 0, 0, 0, 1, 0. So 0, 0, 1, 0. I'm reading from the left. Yeah.
So in this sketch, did you, for xi,
Yeah.
do you store the bits for the branch bits in any of the other x's? Or do you store the branch bits for only that xi?
For only that xi. I mean, so I just defined a function. So each fusion tree node has its own sketch function, depending on all the set of xi's that live in that fusion tree node.
Yeah. Only
Okay.
for that node I mean.
Yeah.
So
Yeah.
for x0,
Yeah.
will you store the branch bits in which x0 is not involved at all? Like the branch bits?
Yeah, you will.
You will, right?
So
Okay,
there's a set of branch bits which matter for that node,
okay.
and all xi's in that node will be projected to those branch bits,
Okay.
even if it's not where xi itself branched. Does that answer your question?
Yeah. Thank you.
Okay. So okay, good. So the 0th and the 3rd bits from the left are the ones that are relevant here. Those are the branch bits. So here it's 1, 1, 1, 0, 0, 1, and 0, 0. Okay, that's the sketch of every single one of these. And then now some query can come in, which could be totally different. Okay, so well, let me show you what I mean. So imagine a query comes in like this, like this, like this, and like this. So this is 0, 1, 0, 1. This is our query. Okay. And what's its sketch? It's 0, 0. Okay? So in actuality, Q should be between, remember that the reason we're trying to find out where we fit in these xi's is to know which subtree to recurse to. So really, Q should fit in the subtree between these two items. That should be where we're going down to. But, no. It should be going down in the subtree between these two items, right? Because the query node is actually between this and this. But its sketch makes it look like it's between these two, right? So that's not good for us. Okay. So that's the first thing we're going to fix right now before we move on to fixing other things. It's going to be, I think, the easiest thing to fix. Questions about anything so far? Okay. So, and if the insight here is to look at the first bit where things went wrong. And what do I mean the first bit where things went wrong? I mean things went wrong because we weren't storing a branch bit that we really should have been storing. Okay. And that's right here. Right. Up until that point, the branch bits we were storing, namely this one, were keeping us on the right track. But then Q branched somewhere where we didn't, keep information. So suppose sketch of Q lies between sketch of xi and sketch with xi plus 1. Okay. It does not imply that Q lies between xi and xi plus 1, but I claim that we can still use this information for our benefit. Okay. And the way we're going to do that is as follows. Let y be the node where Q falls off the highlighted paths, namely the first node. So this is our y here. Okay, and there are two cases. Either Q is going to fall off and go to the right, or it's going to fall off and go to the left. Okay. So if Q falls off to the right, set E is going to be a new word to be y. By y, I mean, look at the bit string, the prefix that's defined by this node. So here y is just 0, because we went left 0 once. Okay. This node would be 0, 1, for example. we'll let E be y followed by 0 followed by a bunch of 1s. Okay. Otherwise, if Q falls to the left, let E be y1, 0, 0. Okay. And the claim is if we see where sketch of E fits amongst the xi, okay, that is the same among the sketch of xi's or even E itself, that is the same as where Q fits amongst the xi, which is what we actually want. Okay. So the way we're actually going to do this is we're not just going to recurse into the two things that the sketch fits between. Okay. But when we find where the sketch fits between, we're going to form this E. Then we're going to again run a comparison with this E. And then we're going to use that result to tell us where to go down. Okay. Are there questions about what we're doing? Yeah.
How do you find where Q falls off to the right?
Oh, that's a very good question. Okay, so that's where. So I claimed that if we had number 4, we could do that. So do people agree? How would you use this number 4 to? We haven't done number 4 yet, but yeah.
You take the MSB of the knot of the bitmap, like ones represent nodes in the map, nodes that we're masking out.
Wait, sorry. Say it again. Of the knot.
I mean, it depends on how we're representing the mask, like whether the ones, the nodes that we're keeping or the ones that we're discarding. But either one, you take like the MSB will give you the node where it falls off.
Yeah, oh yeah. Let's pretend in terms of the masking. Let's pretend that we actually somehow were able to compute the sketches properly. Okay. We already have the sketches.
Oh, yeah.
So right. So now, yeah, we already have. Oh, okay. Yeah. So we have the sketches, but we also have the xi's too. Okay. So we have both of them. So now what would you do? Okay, so let me write that here. So first of all, this proof, I'll leave it to you as an exercise. But you're saying that to find y, okay, you do what? xi XOR, is that XOR? It is. Q, okay. Right. Yeah. Okay, people agree. People see what's going on here? So xi XOR q is telling you the bits that are different, okay? And the most significant bit is telling you the first bit that's different between the two. Okay. And I'm sorry? You would do yeah, no, you're right. You would do this to the actual xi, as you were saying. You would do this to the actual xi. And you would do this to both xi and xi plus 1, okay, to see where you first fall off. Okay? So compute the most significant bit of xi XOR q and the most significant bit of xi plus 1 XOR q. Okay. And then just take the more significant of the two. And that would tell you the first time you fall off between the two. Okay. And here we're just using the fact that that bitwise XOR is just telling you which bits are different. Right? Okay, so we're gonna have to eventually come back to dealing with how to actually do most significant bit, but we're gonna do that at the very end. Okay. Any other questions? Yeah.
So in this example, it falls off to the right, and it lies in between xi plus 1 and xi plus 2. That's always the case that if it falls off to the right, it's going to lie between xi plus 1 and xi plus 2.
Let me think. I mean, but it could. Okay, I guess. So let's say what you actually know, right? So you know the sketches. It could be from the sketch. Yeah. So okay. So when you're falling off to the right, I agree with you, I think. But you still have to compute this y using this most significant bit. Like, how do you know what y is, which is the original question. Right. To know that you fall off to the right, you would have to know what y is.
No, I guess my question is what we need to bother like finding all of the
Oh, I see.
if we can just find it that way.
I see what you mean. Yeah, I think what you're saying sounds plausible. This might be the case, yeah. Okay. Any other questions? Okay. So anyway, so that's how we use sketching to help us find where we should recurse to. But of course, there's the issue I raised in the very beginning, which is we don't have a C operation which makes sketches for us. Okay. So here we're going to use, we're going to start getting into the power of multiplication. Okay. And why did I choose this w to the 1/5? Right now we're using way less space than we need to use. I mentioned that sketches fit in w to the 2/5. Okay. So problem. How do we form sketches? Okay. And the idea here is we don't need to actually do sketching exactly as I said it. So one way to do sketching is just to mask out the important bits, the b sub i's. Okay? That we can do just by a bitwise AND with a certain string we create in preprocessing. The problem is that doesn't do any compression. After you do the AND, you still have w bits left. So perfect compression would get us down to this w to the 5th. But we don't have to get w to the 5th either. We're allowed to be somewhat looser. Okay? So we don't want w, but we can get away with worse than w to the 5th. So we'll compress down to r to the 4th bits. Okay, so we won't get r bits, but we'll get r to the 4th. R to the 5th is w. We don't want w. Okay, and the important bits will be represented with some known amount of zero spacing in between them. Okay.
What's the problem now? What's wrong with masking and
So if you mask, it still takes W bits,
okay?
and the number of items is W to the fifth. You're still taking W to the 6/5 space, bits of space.
Right.
I want to do some amount of compression.
Right. So this is all preprocessing, right?
Yep.
So we can compress by shifting and adding. Like, well, what are we concerned about right now? Is it the time?
Okay, so it's true that we can preprocess the XIs to make them look nice in their sketches, but Q is coming online as a query.
Right.
So whatever sketch we do has to be applicable to Q in constant time as well.
Okay.
Does that answer your question? Yeah. But that's a good point. Yeah. In preprocessing, we could make these perfect sketches that took exactly R bits on the XIs, but then when a Q comes, it's not clear how to sketch that on the fly. Yeah.
And also we must be able to compute MSB of xi XOR q. And we are not storing xi's explicitly.
Oh, we will.
We will.
Yeah. We'll store them and we'll store their
And the
sketches.
sketches.
Yeah. But we won't store the fully compressed sketches. We'll store some sketches that have some amount of spacing in between, but they'll still take at most R to the 4th bits each. Yeah.
So if we're storing the full XIs, why are we storing the sketches also? What is that?
I mean, the way that we'll define sketches, you can compute the sketch function in constant time, so you don't need to store the sketches. I mean, you could compute them on the fly when you need them, but it'd still be linear space even if you stored them. Like for each XI, storing it and its sketch would just be an extra.
Couldn't you also do the computation with the stored XI that you have without ever? I mean.
Okay. So, right. So we're still not to the point yet where I've told you exactly how we're representing a fusion tree node. But the point is, whatever we're storing in that fusion tree node, when a query element comes into that node, it needs to decide in constant time where it's going to go. So there are going to be certain, carefully crafted words, just a constant number of them, that we're going to, in pre-computation, we're going to place in that node, so that we can do that decision in constant time. So I haven't told you what exactly we're going to store in that node, but it's going to involve the sketches of those XIs. Okay, and we're going to get there soon. So this word level of parallelism is to do kind of parallel comparison. So at some point, Q is going to come in, and in constant time, we're going to decide exactly how many, which index it lands between. So we're going to have to compare against everybody kind of at the same time. Okay. So, question?
The question is, how do we deal with ties? So say once you have
Well, it looks like E would give you like 0, 1, right?
E? E would give you, so E itself would be, where's Y? So Y is 0. It'd be 0, 0, 1, 1, 1. It'd be the rightmost thing in this tree.
say your query was like 1, 0, 0, 0. Then E would become 1, 1, 0, 0.
Say E were
So
1.
Say your query was 1, 0, 0, 0.
Okay.
Then E would become 1, 1, 0, 0.
Then 1. It would be 1, 0, 1. It would be 1, 0, 0, 0, 0. Wait, hold on. So you're saying, let me just make sure so you're saying suppose the query instead were
1, 0, 0, 0.
So suppose your query were this. Okay. So you fell off. So where's the first branch node you fell off?
You fell off at 1, 0. So Y is
1. Here. Well, this is a branch node though.
yeah. No, you
You
fall off
fell
at
off the second.
But this is also, yeah, correct. This is not a branch bit. Okay, good. So this would be your Y.
And then, so E would be Y 0, 1, 1.
But your sketch is 1, 0, right?
So you fell off to the left, which means that E should be the,
Or 1, 0.
what? Yeah, it should be
1,
that.
1, 0, 0.
So it should be 1, 1, 0, 0. So this would be E,
Yeah.
right? OK. But this is not a problem, right? Or
We can compare against the xi's. So once we know I, we can compare against xi and xi plus 1 to look for tags.
I think this is not a problem. And are there any other questions, or should I keep going? Yeah.
Well, when you say like see where the sketch of E fits among the sketch of the xi's, so it's like the sketch of E is the same as one of the xi's.
Yeah.
Which way do you go?
Right. So at that point, you could do what Anujan said and just actually compare those. There are only now like kind of two possibilities.
Right.
So you just can compare them and see. Yeah. Okay. So now we're going to use multiplication. Okay. So here's the idea. Pick. So suppose we multiply x times some m. Okay. Where x is equal to the sum I from 0 to r minus 1. So let's say we've already now masked out to only keep the important bits. Okay? It's the sum of some xb times 2 to the bi. And y is equal, and m is equal to sum over I from 0 to, we're going to have only one r positions in this m, 2 to the mi. Okay? So the question is, how do we choose? We're going to choose the mi to get something nice. Okay? And the bi's are increasing. The mi's, don't think of them as increasing. The mi's are arbitrary. So lemma, we can choose the mi such that A, for all ij, well, the set, oh, let me write it like this, okay. All the bi plus mj are distinct. So there are r squared of these sums. B, b0 plus m0 is less than b1 plus m1 is less than dot dot is less than br minus 1 plus mr minus 1. And C, if we look at the range, how many bits are spanned from the biggest index to the smallest index, that's going to be r to the fourth. So br minus 1 plus mr minus 1 minus b0 plus m0, that should be O of r to the fourth. Okay, and before I prove the lemma, I just want to say why this is going to be relevant for us. Okay, so the point is that, so let me write the point. Okay, is that x times m is equal to, if you just expand out that product, it's the sum from I going from 0 to r minus 1, the sum j going from 0 to r minus 1, of xb 2 to the bi plus mj. Right? Now, as long as the bi plus mj are all distinct, none of these powers are the same, so we don't have to worry about carries. Okay? And now, once this holds, basically what we're going to do is we're going to only use these R bits. Our sketch is basically going to be projecting onto these locations, B0 plus M0, B1 plus M1, etc. Okay? And we're going to mask out everything else. And notice that the range between the biggest location and the smallest location is only R to the fourth. Okay? So after we're done masking, we can shift everything down so that now this fits into a sequence of contiguous bits starting from the right that's R to the fourth long. Okay? So we have to do this. Okay, so yeah, questions?
Yeah, so you said the MIs may not be increasing. So the range, is that BR minus 1 plus MR minus 1?
Yeah, but there's property B, which says that the sums are at least increasing.
Sorry. Yeah.
Yeah.
And shouldn't like BI plus MI all be less than 2R? Because there are R bits in.
BI plus MI less than 2R. BI is not less than R. I mean, sorry. Yeah, BI is not less than R. BI is at most W.
Yeah,
And
so
MI will
they're-
be at most W2.
So they are not R bits, but
It's-
only
it's-
R non-zero bits?
Yeah. It's not the case that this is less than R. It's just that if you look at the range of bits that are important, they fit into a contiguous block of at most size at most R to the fourth. But once that's true, you can shift them down to be the first R to the fourth bits.
Okay. So initially X and M,
Yeah,
are they R bit numbers?
they're W bits.
They're W bits?
Yeah.
But among them only R bits are
So you should.
non-zero.
That's right. So you should think of X. You should think of X as being one of the Xi's,
Okay.
but we've already masked out the Bi's. We're only keeping the important bits.
Sorry, yeah. I
And-
thought you were sketching.
Yeah, and then now we're trying to compress those bits into fewer locations or into a smaller width of locations. Okay. Yeah.
So property B looks like it only considers cases where I equals J. Is that?
That's right. That's right.
Why are we ignoring the other terms?
Because, well, so the ideal sketch of X has R bits, okay? And what I'm saying is these are going to be where we'll read those R bits off from. So if we want if you look at you want xbi for I between 0 and R minus 1. If you want xbi, just look at the power of 2, which corresponds to bi plus mi. That's what I'm saying over there.
So why even? Okay. So we're really just computing the sum, the diagonal,
So I mean, we're actually computing x times m,
yeah.
okay? Because that's the thing we can do in constant time in WordRAM. But I'm picking m in a special way, such that x has its R important bits spread out. They could span the entire W bits. There could be some huge gaps between them. But after I do x times m, and then mask out only these locations, these R locations, what I'm telling you is that those R important bits are now compressed into a width of length almost R to the fourth, which is W to the 4/5. So they started off spread in a width of W, now they're down to W to the 4/5.
So how are you going to get the masked out?
In pre-processing, we're gonna see how to find this m in the proof of the lemma. So in pre-processing, I'm gonna find this m, okay, and then I can create the mask in pre-processing. The mask is a single word, right? It's a single word which just has ones at these R locations, and to mask those out, I just do a bitwise AND. Right? So I'm gonna do x times m. And then I'm going to do a bitwise AND with the mask containing these R locations. And then I'm going to shift it down. That's going to be my actual sketch. Yeah?
Does this lemma need MIs to be the permutation of the BIs?
The MIs, no, they're not. They can be anything. Yeah. Yeah. Any other questions? Okay. So yeah. So what's the point here? The point is we first mask the BIs, mask the important bits from Xi. Then we do to get X. Then we do X times M. And then we mask out the bits BI plus MI. And then now we shift down so that B0 plus M0 maps to bit 0, to the least significant bit. So we're going to shift down by B0 plus M0 at the end. And then this thing tells us that now it fits in R to the 4th bits. OK, so let's prove the lemma. So we're going to do part A first. OK, so part A. So we're going to prove by induction. Suppose we've already picked M1 prime, M2 prime, MT prime, or T minus 1 prime, such that all the sums BI plus MJ prime, so these are not going to be the final M's, but these are the MJ primes, are distinct mod R cubed. Okay, where T is less than R. Now I'd like to pick, now we want to pick MT prime. So the thing that I want to show by induction is that we can choose M1 prime up to MR prime minus 1, such that all the sums are distinct mod R cubed. Okay? So now I want to pick MT prime. And in order to make sure that all these sums are distinct, we need to make sure that MT prime plus BI is different from BJ plus MK prime. I'm already using K, plus MQ prime, Z prime. Okay, so MT prime must avoid MI prime plus minus BJ plus BZ for all the other different values I, J, and Z. But how many of these values are there? How many of the B's are there? How many BI's are there? So this is R squared, and then there are T of these so far. These T squared R values. But we can work over R cubed values. This is less than R cubed, because we're not done yet. Which means that there's something we can pick which avoids all of these. Okay, so we can choose these MI. We can choose all these MI primes to make the sums distinct mod R cubed. And then now, how do I actually choose the MIs? We'll set, and I'll draw a picture. We'll set MI to equal MI prime, okay, plus I times R cubed plus W minus BI rounded down to the nearest multiple of r cubed. Okay. So the picture to have in mind, this is the final picture that we'd like to have. Is that we have these blocks of length r cubed each. Okay. And all of these mi primes are values between 0 and r cubed minus 1. Okay. And so we have some bi. The thing that we want to have is kind of b0 plus m0 is somewhere in here. b1 plus m1 is somewhere in here. b2 plus m2 is somewhere in here, et cetera. Okay. That's why we add on this I times r cubed to shift us over by r cubed each time so that things are in different blocks. Okay. But so it's true that bi plus mj primes are distinct mod r cubed because that's how we formed the mj primes. But in order to make sure that with the m's they're still distinct, right? That's why we did this rounding down to a multiple of r cubed, because it's mi prime plus that's a multiple of r cubed and that's a multiple of r cubed. So everything mod r cubed has stayed the same. And that means that bi plus mj mod r cubed is different. So in particular, bi plus mj are different. Okay, so that's why we satisfy property A. They're distinct even mod r cubed, so they are distinct. Okay. And kind of this, we want this property that b0 plus m0s are increasing. Okay. So, well, yeah, I mean, they're all, I guess the picture I said is exactly what this does. Maybe you can, I don't want to spend time on tedium, but this picture will exactly put kind of one guy in every single block. Okay. So,
What is the rule of W minus BI?
kind of subtracting BI would just make things negative. So we put the W to prevent that. Yeah, this might take up a constant. It still will take a constant number of words, but that's okay for us. Right. And there might also be some junk here that we don't care about, and also some junk here that we don't care about. But at the end, we're going to mask and shift everything to the right anyway, so we don't care. Okay. Okay, so that's how we're actually going to do sketching. So now, so I defined how to do a sketch. And we can actually do the sketch in constant time, because to do the sketch, it's what? It's a mask, a multiplication, another mask, and a bit shift. So a sketch is like 4 operations, each taking a constant number of words. Okay. Good. And in pre-process, okay, so now going back to a question that I guess you asked me a while ago, what are we actually going to store at a fusion tree node? Okay, so now that we have sketches, suppose node, fusion tree node has x0 less than xk minus 1. One thing we're going to store is the following word, which I'm going to say the sketch of that node is equal to one, the bit 1, followed by the sketch of x0, 1 followed by the sketch of x1, and then 1 followed by the sketch of xi minus 1, xk minus 1. Okay. And now we want to know, a query Q comes. Where does Q fit? Which subtree should we recurse on? So I'm going to define the sketch of Q, the sketch to the K of Q, as being 0 sketch of Q, and right, okay. 0 sketch of Q, 0 sketch of Q. And what am I going to do? I'm going to subtract. Okay. So tell me what happens within a block. So definitely there will be no carries going from block to block because just this part is bigger than this part because that's a 1 in the most significant bit and that's a 0. Okay. What am I going to get? I'm going to get either a 1 or a 0 followed by some stuff that I don't really care about. A 1 or a 0 followed by more stuff I don't care about. Okay. And then I'm going to mask out all of these. I'll get a 1 or a 0 followed by zeros, a 1 or a 0 followed by zeros, and then a 1 or a 0 followed by zeros. By the way, so I'm forming this in pre-processing. Q comes on the fly. How do I form the kth power sketch of Q? Yeah, right? You multiply by a number that has 1 here followed by zeros, 1 here followed by zeros, 1 here followed by zeros. Okay? So that's a single multiplication. Okay. And now, if I want to know where I land, what do? I take the most significant bit. Okay. And that's correct. But I'm going to do it a different way. Okay. And the reason I'm going to do it a different way is because the way I'm going to do it is also going to play a role in how we actually do most significant bit later. Okay, so there'll be some circularity if I say do most significant bit here, and then when I say I do most significant bit, I'll say do it like how we did it here. Okay, so. And the key insight is kind of the number of kind of bits here that we care about there are k of them. So if we can, and it's monotone, right? It's going to be, so let's say it's going to be, I guess, these are the smallest numbers. These are going to be, what should I say? When is this a 1 and when is this a 0? It's a 0 if we had to carry this 1. We carry this 1 if this sketch is less than that sketch. So this is a 0. This bit is a 0 if the sketch of Q was bigger than the sketch of x0. So it's going to start off as 0 for a while, and then it's going to be a 1. And that first 1 is going to be the first thing we're smaller than. Okay? That's why finding the most significant bit is the right thing to do. So the point is that this is monotone. So finding the position, and there are k of them, so finding the position of the first one is the same thing as counting the number of ones. If we know how many ones there are, that tells us where the first one is. And how are we going to count the number of ones? We're going to multiply. Okay, so so the appearance of ones is monotone. And that implies can just count the number of ones to find the index of the first one. So remember, we want the most significant bit of that thing. So what we're going to do is we are going to multiply by, let me make sure I don't tell you the wrong thing. Yeah, I guess it's just this thing. 1, 0, 0, 1, 0, 0, 1, 0, 0, and then 1, 0. Okay, we're going to multiply by this thing. Okay, and what that's going to do is it's going to take this. So this 1 here, right, will appear here. If you multiply that, it'll appear here, 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 and here if it's a 1. And that will get added. So then if this is a 1, that 1 will appear here, 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 etc. And the point is, when you do the multiplication, all the things that are 1 will contribute by adding starting at this position. Okay, so all the 1s contribute by adding to that position. So then what you can do is, and they don't interfere with each other because this count is a number between 0 and k. So it's going to consume at most log k bits. Whereas what's the width of this block? The width of this block is like k to the 4th or something. Okay, so there's no chance that these things are going to clobber each other. Okay, so what you do is you look at a log k width interval of bits around here. You mask everything else out, and you shift this down to the beginning. And that number is exactly the number of 1s. Okay. Good. I think that's the word level parallelism, what I meant by parallel comparison. Right? Basically, we compared everything at the same time in a constant number of machine word operations. Okay, so now the only thing left is computation of the most significant bit. And the way we're going to compute the most significant bit is, again, using multiplication, sketching, and word level parallelism, as well as this idea. Okay? So now that you are masters of all these ideas, I'll just sort of tell you how this goes. So the basic idea is split. So let's say we want MSB of x. Okay, we're going to split x into root w chunks of root w bits each. It's not going to be recursive like Van de Boas. This is just a one-time thing. Okay, so for example, if I write x being 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1. So here, w is 16, and root w is 4. This is the first chunk, this chunk, this chunk, this chunk. And what we're going to do is first using like word level parallelism and multiplication, etc., we're going to figure out exactly. We're going to form a root w length bit string that's consecutive, which will tell us exactly which clusters are non-zero, which clusters have anything in them at all. Okay, and then once we find that, we're going to find the first non-zero within a cluster. And we're going to, at some point, exploit the fact that we can deal with root w size numbers we can do crazy things to them really fast. Okay? Okay. So good. So the first thing is I'm going to create f, which is 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. Okay, why am I doing that? I'm going to do x and f, bitwise and. Is that bitwise and? I don't know. Okay. Yeah, that looks too much like XOR. So that is going to look like this. And let me, right after I write it, I'll tell you why I'm doing this. So what I'd like is some summary that tells me which clusters are non-zero. I'm going to treat the first bit as a special case. Okay. So now I know for sure that this cluster has a non-zero and this cluster has a non-zero. In particular, because they have it in their first bit. Okay. So I'm going to deal with the first bit of a cluster and the remaining bits in a separate way. And the reason I want to do this is because, remember when I did the parallel comparison, I exploited carries and subtraction, right? And in order to do that carry and subtraction trick, I needed to have room to have an extra 1 bit at the beginning of every cluster. So now I'm going to clear. Now that I have this information handy, which I can look back at later, I can clear it and deal with everything else. So now I'm going to do x XOR x and f, which just clears all the leading 1 bits. So we'll have 0, 1, 0, 1, just like this. We'll have 0, 0, 0, 0. We'll have 0, 0, 0, 0, because we clear the leading 1s. And then we have 0, 1, 0, 1. So we clear the leading 1s. Okay. And now what I do is I will take I will take f minus that thing. Okay, so what does that look like? So f looks like 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. And x, bitwise XOR x and f, looked like, well, it doesn't have any 1s in the leading positions. It looks like 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1. And I do a subtraction. Okay. Which blocks? So within each block, definitely the f block is bigger, because it has a 1 in the most significant bit, because we cleared those in the x thing. So the cases where this 1 gets borrowed are exactly the cases where the block is non-zero. If the block is non-zero, it gets borrowed. So here it will get borrowed, and it'll have 0 times some junk we don't care about. Here it doesn't get borrowed because it's empty, so we have 1 and some junk, 1 and some junk, 0 and some junk. Okay. And now we mask and get rid of the junk. And then we have 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0. Okay. We masked out all the junk. And then we OR back in that. Right? Why do we OR that back in? Because this tells us which clusters are non-zero, but I lost all information about the leading bit in the cluster. Now I want to get back that information about the leading bit. Right? So I OR back in x and f. And then I get 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. Great. So now I know exactly which clusters are non-empty. The clusters that have a 1 in the leading position and 0 else. So this cluster, and this cluster have stuff in them. Yeah?
Don't you want to negate the zeros and ones in the first place?
Yeah, that's right. I should do That's right. I should do a mask and a not as well, right? I should not and then mask. Yes. Yes, I could also XOR with F. That's a good point. So, yeah. And then I XOR with F, and then because 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. Yeah. So now this should actually have been a 1, I think, and that should have been a 0. Well, something like that. But yeah, you should have negated and then masked out. That's a good point. But the bottom line is we have these root W size chunks. Each one has a 1 in the leading position if and only if that cluster was non-empty. So now what I want to do, now what I'm going to do is I'm going to sketch. But I'm not going to do a sketch into r to the 4th. I'm going to do a perfect sketch. And it's going to be, again, via multiplication. Lemma. So the point is, originally the BIs were just arbitrary. Who knows where the important bits were, right? They depended on the branch bits. Now we know what the BIs are. They're root W minus 1, 2 root W minus 1, 3 root W minus 1. Okay, so when the BI are I root W plus root W minus 1, there is an M such that multiplying by M makes all the important bits consecutive with no gaps. Okay. Proof, I think that will end up being on your homework. So now what do we have? We're almost done. Now what do we have? So I'm telling you that I can form a word that has this 1, 0, 1, 1 consecutive. One, 0, 1, 1, which is just the leading bits in each of those clusters. In constant time, right? We can do that by multiplying by M and then doing some shift and masking. Okay. And then now what do I do? Now I need to know what's the most significant bit in this word. That tells me the first cluster that has a non-zero, right? I want to know the first cluster that has a non-zero. So do parallel comparison between this 1, 0, 1, 1 and the set of words 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Each one is root U wide. They're root W wide. They're root W of them. They fit in a word. Even when you put those extra 1s in between, remember to do parallel comparison, you had to put these 1s and 0s as stop measures. It still fits in 2 words. Okay? And you do a parallel comparison with this vector repeated a bunch of times, you'll find it out. Now you know the index of the first cluster. So the first cluster happened to be this one. Now what do you do? Again, that fits in root W bits, right? You can just shift that down. And again, you do a parallel comparison with these root W things. Okay. And then I know my most significant bit. So that's all the details, except I didn't prove the lemma, which I guess you'll prove yourselves. So I think that's the end of fusion trees. Yeah, so, yeah. All right. I'm not sure. How do you form this? How do you form this? You multiply by a word which has 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. I'm sorry? Right. But we know how to do that because, right, so we said that we can find E by doing a most significant, yeah, that's right. Do this with E.